So we're going to compare two bases for a given vector space, and we've just proved the so-called exchange theorem. Right? The exchange theorem says if you have a basis and you have some other vector that has a non-zero coefficient when you write it as a linear combination of the basis vectors, you can replace that the basis vector corresponding to the non-zero coefficient with this new vector, right? And what we're going to do is use this exchange theorem again and again to compare the size of two bases. So, we're hoping that any two bases have the same number of vectors when we're talking about finite sized bases. So let's be optimistic and say that we will be able to prove this. We will be able to prove it. Okay, so let's suppose that we have two bases, say B, made up of betas, say beta 1 through beta n, and another basis, let's call it C. So maybe, how about gamma 1 through gamma k? Now, we can't assume that the number of gammas is the same as the number of betas, because that's what we're trying to prove, right? Our hope is that we can prove that k is equal to n. All right. So, so let's start exchanging gammas for betas. All right, so gamma 1 is in the span of B, right? Because the span of B is just our vector space, right? B is a basis for our vector space, so it has to span the whole thing. So we can write gamma 1 is some linear combination of the betas. Right, like this. Plus a sub n, beta sub n. And one of these a's is non-zero, right? Because gamma can't be the zero vector, because otherwise C wouldn't be linearly independent, and C is a basis, right? Both of these are bases. I should write that down. These are both bases. So gamma 1 can't be 0, and so one of these a's has to be non-zero. So replace beta sub I with gamma sub 1. All right? That gives us a new basis. So let's call the result I guess B hat, maybe? Okay, so next thing we're going to do is do the same thing, but now with gamma 2. Gamma 2 is also in the span of... So the exchange theorem tells us that beta hat is a basis for V. Actually, let me call this B sub 1, because we're going to have lots of bases floating around. So B sub 1 because we've done one replacement. Okay, now gamma 2 is in the span of B sub 1 because, after all, we know B sub 1 is a basis for V. So that means that we can write gamma 2 as a linear combination of vectors in B sub 1. Right, well, we have to be careful here because B sub 1 is mostly betas, but B sub 1 does have a gamma in there somewhere, right? But what I want to claim here is that in this linear combination of gamma 2 as a linear combination of vectors in B, the coefficient on gamma 1 can't be the only non-zero coefficient. Okay, why is that the case? Well, suppose that it were. If the coefficient on gamma 1 were the only non-zero coefficient in this linear combination of, right, we're writing gamma 2 as, see, I'm hesitating to actually write out what this would look like as a linear combination of the vectors in B sub 1 because we don't know exactly what position gamma 1 has taken, right? We don't know which beta it's replaced. And so actually writing this is going to be a mess, so maybe I won't do that. All right, so if the coefficient on gamma 1 were the only non-zero coefficient, then our linear combination would look like this. We'd have gamma 2. Now we're writing gamma 2 as a linear combination of vectors in B1, but we're saying all of the betas have coefficient 0. The only non-zero coefficient is on gamma 1, and so it would look like this, with A1 not being 0. But remember that this all of the gammas are linearly independent. So this can't happen. What we've done here, right, what we've done here is written down a non-trivial linear dependence relationship between gamma 1 and gamma 2, but the gammas form a basis. This can't happen. So that means that my claim here is true. The coefficient on gamma 1 is not the only one that's non-zero. So what we can do is choose some other non-zero coefficient say for the coefficient for beta j and replace beta j in our basis B1 with gamma 2 to form a new basis B2 for our vector space V. So B2 is all of the betas except we've replaced one of the betas with gamma 1 and another one of the betas with gamma 2. We don't know which two betas, right? I called them I and J, but we don't know where those are in the list. Well, you can see that this step here, now that we've done this for gamma 2, we can do this for gamma 3 now. So rather than rewrite everything, I'll just change all the indices. So now take gamma 3. Gamma 3 is in the span of B2. Write gamma 3 as a linear combination of vectors in B2. Then the coefficient on gamma 1 and gamma 2 can't be the only non-zero coefficients, because if they were, that would mean gamma 3 was a linear combination of gamma 1 and gamma 2, but that is impossible because the gammas are linearly independent, and so we can choose a non-zero coefficient on one of the betas and in B2 and replace that beta with gamma 3, and this forms a new basis B3, right, for V, right, because this is the exchange theorem again. Well, you can see that now that we've done it for gamma 3, we can do it for gamma 4 and then gamma 5 and so on. So just repeat this process over and over again. Now here's where we use the finiteness. Since B and C are finite, this process has to stop. At some point, right? Either we run out of betas to replace, or we run out of gammas with which to replace betas, right? Now we're in one of two situations. If n is bigger than k, I think I called it k, yes, So if n is bigger than k, so in other words, we have more betas than gammas, right? So if n is bigger than k, then our last basis, which I guess is going to be b sub k, this last basis we formed by doing this replacement process looks like, I need an angle bracket. Our last basis looks like gamma 1 and so on, right? We've done enough replacements that we've got all the gammas, but there's at least one beta left over. Now we don't know which beta it is, but there's at least one, right? Maybe some more. Okay, but this means if this were the case, right, this last beta has to be in V, of course, but V is in this the vector space V is the span of all of the C's, or sorry, the span of C, right? The span of all of the gammas. So since B is in the span of the gammas, that means we can, since beta is in the span of the gammas, that means beta is some linear combination of the gammas. Of course it is, since the gammas span the entire vector space. But then, this means that this set B sub k with the gammas and the beta can't be linearly independent, because we've written down a non-trivial linear dependence relationship, right? But that's a contradiction, right? So that means that n can't be, right? N can't be bigger than k. So that means k has to be greater than or equal to n. Okay, right? Well, now let's suppose that k is strictly bigger than n, right? So in this case, we have more gammas than we have betas, right? So that means b sub k is gamma 1 up through gamma n. And we have more gammas, right? Not in this list is all of the gammas left over. Gamma sub m plus 1 out to gamma k, right? Because we're assuming we had more gammas than betas to begin with. We're assuming k is bigger than n. Well, in this case, if b sub k spans V, which it must. Remember, the exchange theorem, using the exchange theorem over and over again, told us that b sub k is a basis for V. Okay, so if b sub k spans V, which it must, then that means that the next gamma along is a linear combination of gamma 1 up through gamma n. But this is a contradiction, because the gammas were supposed to form a basis. So, right, we can't have one of them being a linear combination of the others, because they have to be linearly independent. So this is a contradiction. So that means that k can't be bigger than n. So k has to be less than or equal to n. Well, right, we already knew that k has to be greater than or equal to n, and so the only possibility left over is that k is equal to n, right? So finally, fair amount of work, but we proved that if you have a finite basis, every basis for that vector space has to have the same number of elements. And that lets us make the following definition. So the dimension of a vector space is the number of vectors in one, and hence any, basis for V. And we'll write this using this notation, dim V, of course, meaning dimension. Right, so If we didn't know that every basis had the same number of vectors in it, this wouldn't be a well-defined thing, right? If it were possible to have one basis with 2 vectors and one basis with 3 vectors, would you want to call the dimension of that vector space 2 or 3? Well, we don't have to worry about that possibility because we know that every basis will have the same number of vectors in it.